My name's Duncan Baker-Brown. I'm an architect, academic. I teach at University of Brighton. I've written a book called The Reuse Atlas. I'm focused on sustainable strategies for the construction world for the last 25 years. I wanted to just set the scene a bit for resourceful material. We're in the world now where these sorts of planned applications can get refused. And also I just think the rhetoric for Future Build this year is exactly where we need to be. And I might draw your attention to one of the action groups that's been set up by architects in response to the climate and ecological emergency. So we got ACAN, who have got a stand over there, and you can go and take part in their carbon confessions. We find ourselves in an environment where 75% of the population of the UK live in regions that have declared a climate and ecological emergency. Not only that, the local authority councils have said they want to be net carbon zero by 2030, which is of course pretty much impossible, but the ambitions to be applauded. Now, why should we care? Well, I care for these sorts of reasons, and maybe you do as well, but these sorts of reasons are really also very scary. So this is a slide I nicked from Vivienne Westwood, and I think you can see that obviously with the fires we've had in Australia, etc., uninhabitable planet Earth is a big deal and an imminent one. So why us in the construction industry? It's because we consume so much. 60% of the UK's waste is created by the construction industry. That's 120 million tonnes of waste a year. We consume 600 million tonnes of products annually. So what next? Well, for a lot of people, it's a bit of this, with a bit of that, and a lot of this at the moment. Is it really worth it? Can we afford it? So we really need to be thinking about managing resources. And this is why, with the fact that humankind in the construction industry consumes 50% of all the raw materials mined and harvested every year, the construction industry is all about managing resources and reducing the consumption of resources. And it's designers that do this. So we've got to take ourselves from a linear economy to a circular one. A linear economy where we take, make, and throw away. And we're not very good at it. That's a photograph of the last 23 North American bison before 10 more were shot. Air quality and carbon emissions are really high. But we have opportunities, and I think the circular economy and closed-loop systems and sustainability on the whole provides us with that. I wrote a book about it, which has got 30 case studies of projects dealing with recycling, reuse, reduce, and the holy grail of proper closed-loop systems. The construction industry's halved the amount of waste over the last 10 years that it sends to landfill and incineration, and WRAP estimates that nearly 20% of the construction industry is already circular. And this is perhaps the best slide so far. We are reducing the amount of coal we're burning. And it's our cities that give us hope, I think, because I believe it will be these city-states that set the standard. They are at the moment with their net carbon targets of 2030, the net zero targets. That's within the context of building regulations that are nowhere near asking for any of that, and that's why there's been a big debate about Part L at the moment. So my point is that we need to mine the Anthropocene, rework the stuff that either grows or we've already produced. Mine the Anthropocene. And stop making sustainability the Mickey Mouse issue. Okay, and I think this is the last slide. We need to consider refusing projects before we reduce the amount of stuff we use when we design and construct projects. We need to then reuse material whenever possible, and that includes retrofit, obviously. And then last of all, we recycle, because recycling's okay, but it creates pollution and waste. So our biggest challenge is not changing today. Thank you very much. That was a bit rushed, but we got to get on. I want to introduce you to Nick Gant, who's my colleague from the University of Brighton, and he's going to chair the first session.
Good morning. Thanks, Duncan, for a fantastic intro, as always. Welcome, everybody, to Future Build and to the Resourceful Materials Zone. We've got 5 fantastic speakers for you this morning that really focus on this notion of resourceful materials. And moreover, I think The vast majority are looking at some of what we consider to be the kind of new epoch of growing materials, maybe growing materials locally to allow us to share knowledge, but keep materials close by, close to hand. Our first speaker today is Mark Lynn. Mark, we've worked together on a EU project looking at sustainable materials that either come from the city or can be grown nearby to the city. So I'd invite you up to the stage here. We're going to give everybody a kind of 10-minute period to speak, which will hopefully give the floor the opportunity to ask them all questions at the end, and we'll invite them all back then. So, Mark, if you'd like to fire away, you've got everything you need there, sir.
Get the clicker.
Ah, where's the clicker gone?
Sorry,
Duncan nicked it. Of course he has. You can take the man out of Essex. All right, okay.
That's all right.
Thank you, Mark. I'll give you a 2-minute warning if that's all right.
Thanks, Nick. I'm speaking today on behalf of the Natural Fibre Insulation Group of the Alliance for Sustainable Building Products. The group is a collaboration of the main natural fibre insulation brands that are members of the ASBP, and our aim is to promote and educate and inform about the use of natural materials in all their forms for insulation. Duncan mentioned it in his introduction. He used the term Mickey Mouse. I'd just like to point out that all of these brands have been around for over 20 years. Most, if not all, are manufacturing at scale and are scalable. So these products have got an established technology, established track record, and are a viable solution today. If you want to go on the ASBP website, you can see some resources that we've produced on natural fibres, information sheets, presentations, etc., and that's a growing body of work. So if you go on the ASBP website, you'll be able to learn a bit more. So if we look at the natural fibre itself, you can see that it does many things. It's a heat buffer. It's an efficient insulator. It acts as a carbon store. It's a pollutant filter. It's a sound absorber. And that helps make it ideal for insulation. Because, of course, when we think of insulation, we just think of heat loss. But, of course, insulation does much more than that. Insulation can account or amount to at least 50% of the volume of the building fabric. It has benefits in terms of every aspect that I've highlighted there, really. So when we think of insulation, we've got to see it as a multifunctional component of the building fabric. And I'm just going to run through the aspects of insulation and what makes natural fibres particularly good when it comes to each aspect of that. So I've put at the top there a heat buffer. So if we then look at a heat buffer, what do we mean? Well, what we're trying to do is to make sure that the peak heat outside a building and the peak heat inside the building are shifted out of phase with each other, because the last thing we want is the inside of the building to be as hot as the outside of the building in the middle of the day. And in order to do that, we have to shift those peaks out of phase with each other. And the best way to do that is to use a material that's got relatively high thermal mass, relatively high specific heat capacity, and low thermal conductivity, all of which you're going to get from a natural fibre. So what that means in practice is that as we have a high external temperature, the insulation itself is absorbing heat and it's pushing the peak temperature away. In fact, what we're trying to do in a 24-hour cycle is move the peak external heat and the peak internal heat as far away from each other as possible, which is a 12-hour shift in the phase. And we can achieve that with a natural fibre insulation. You can see with a mineral-based product, you're only shifting that phase by about 6 hours, so it's not enough, really. We then look at natural fibres as a moisture buffer. It's all right. there's a lot of materials would describe themselves as breathable, and I suppose I can understand why, because it's a very intuitively positive thing to be breathable. But natural fibers natural fiber insulation is breathable in a true sense, in that the fibers themselves aren't just vapor open, but they absorb and release moisture and hold that moisture in a physically bound form that make the moisture much less active and much less prone to doing damage. And then they can release the moisture again. So moisture is held by natural fiber in three ways. One, very tightly, which is sort of permanently in the fiber. And then some water is held very loosely, and it's sort of absorbed a little bit and released a little bit. But you've got this sort of Goldilocks zone in the middle where the water can be easily absorbed, held safely and easily released, and that's where the real breathable benefit of a natural fiber comes in. The main benefit of breathability is to help maintain humidity within a safe level within the building, and I'm sure many people are familiar with this diagram, but it's very important to keep relative humidity within that optimal zone, because it inhibits a lot of negative impacts from bacteria, microbes, degradation within the building fabric, etc., etc. What happens is the natural fibers themselves will constantly adjust their humidity to be in balance with the surrounding humidity and adjust surrounding humidity to be in balance with theirs. And that's really important when it comes to insulation, because heat and humidity are very closely linked. As I mentioned earlier, the water molecules bind to the proteins or the carbohydrates in the natural fibers like magnets, and it holds the water in a very safe form. Source control in emissions, VOC emissions from building materials, is becoming an increasingly important issue, and rightly so. I've got some examples here of thermally bonded sheep's wool, thermally bonded flexible wood fibre, and wood fibre boards, looking at total VOCs, carcinogenic, mutagenic and reprotoxic substances, and formaldehyde as well. And you can see for both of those, or all three of those products, the levels of emissions are extremely low. If you look at sheep's wool in particular, sheep's wool can actually chemically neutralize formaldehyde. Formaldehyde is a problem I think a lot of people felt was dealt with in the 90s or the early noughties, but indoor formaldehyde levels are still a big issue. Formaldehyde off-gases from an awful lot of products within the built environment. So having a material that can permanently lock up and remove formaldehyde is a very useful property for anything. And the last slide is on acoustic absorption, because you get the irregular structure and the non-uniform structure and density of natural fibers make them very efficient sound absorbers. So, for example, if you're looking at sheep's wool, you can achieve the same level of acoustic absorption at around half the density that you would need with a rock, say, for instance. I've sort of steered away from some of the eco stuff here, because I wanted to make the point that these are very functional products, that the natural fibers themselves provide the insulation with properties that are over and above some of the better known, more conventional products. And if we're going to shift to an economy or an environment where we're making use of more natural resources, we can't be sort of pigeonholing these as merely an eco alternative. They're not just an eco alternative, they're functionally superior in many end uses. I'm not saying in all end uses, because we have to realize that certain materials are appropriate for certain end uses, but there's certainly in terms of the use in construction, natural fibers, possibly other than structural timber, are currently underutilized. But as I said at the start, these products are being made at scale and are scalable, so there's no reason why we shouldn't, over the next decade, have a significant shift to the use of more natural fibers in end uses such as insulation. Thank you, and I think I'm ahead of schedule.
Fantastic, Mark. Thank you. As I say, I was involved in a big European project that Mark helped us out with, and it's fair to say I don't think I've not come across anybody that has such a comprehensive knowledge of these kind of materials that, like you say, are long-standing in many respects now. So I hope we'll get everybody together at the end, and I'm sure there'll be questions for Mark, which hopefully he can answer. But we're going to move on now, so thank you very much again, Mark, and we'll welcome you back at the end of the speakers. So we're now moving on to Oksana. If you'd like to come and join us here. Oksana is Director of Design at Biome, and I think it's fair to say Biome deal with one of the materials, mycelium, which has kind of captured the imagination of designers the world over, really. And again, is a kind of established material that Oksana and colleagues have expertise in, which is being shared internationally. We had a conversation this morning about, again, this idea of sharing the knowledge, but materials being grown locally and so on, and she'll obviously tell you more about that. So thank you very much, Oksana.
Thank you. Hello. So my name is Oksana, and I'm a Director of Design at Biome. And today, as part of this panel, I'd like to take an opportunity and talk to you about biomimetics and how nature can inspire all of us to revolutionize construction, and how we do exactly that at Biome. But before I do that, I'd like to tell you why we do what we do. And we do this because our built environment... Oh, I'm sorry. It's the video? Sorry, it's the video. There is a video, yeah, before this flight.
That one. Just going to have to do it, run it from here, probably.
So the black.
Yep.
Let's try this again.
Pick it.
Is it playing?
Pick it.
No.
I'll just try it automatically.
Yeah.
Come on.
Okay, and we do this because our built environment, infrastructure of our cities, our industry and transport are the largest contributors to the climate crisis we're in. Our industry is toxic, extractive and vandalizing. Our land is being carved and deforested. Our waste is piling, and our islands, plastic islands and mountains are growing. And according to NASA, last year was the hottest year on record, with the Earth's surface temperatures are rising by 1.1 degrees. And we're on a trajectory to raise this number to 5 degrees by the end of the century. The planet's long-term warming trend has caused wildfires to rage through the planet and freak storms to destroy and displace our communities. We share the Earth with around 15 million of extraordinary species of animals, plants, and microorganisms. And all this magnificent biodiversity is being lost due to land use, unsustainable use of natural resources, climate crisis, and pollution. And today, about 23% of mammals and 12% of birds are considered as threatened, of which many are becoming extinct. Humanity is facing a mammoth but self-inflicted problem. And at Biome, we share the belief that there is a solution, and it has a name: biomimetics. Biomimetics is design inspired by the way functional challenges have been solved in biology. And one of the fine examples of applied biomimetics is the Gherkin building. Its structure was configured by a very intricate but robust form of the Venus basket coral. Nature has faced and resolved many challenges through centuries of evolution and has answers to engineering, design, and systemic problems. If we look closer, we will find that in nature, the concept of waste is non-existent. All nutrients are in constant circulation, all forms are highly functional, and all organisms work with one another in symbiotic partnerships. And the principles of biomimetics have laid the foundation of what's now known as circular economy. So at the moment, we work in a very linear way. We extract, we make, we use, and we dispose. However, when we shift towards the circular economy, this line will start to curve and move in infinite circles, allowing us to design out waste to keep our biological and technological nutrients in constant circulation, which will help us to have a regenerative impact on our environment, society, and economy at long last. And the principles of circular economy are at the very core of what we do at Biome. Biome is a research and development-led company that allows nature to lead innovation to create a much more healthy and sustainable built environment. And we offer a collection of bio-based materials, construction systems, as well as research services to the industry. And one of the first materials I'd like you to meet today is ORB, or Organic Refuse Biocompound. Now, at the core of ORB, or in fact all of our materials, are local waste streams. We transform food and agricultural waste into precious substrates that we then combine with our unique organic binder that, by the way, is made of edible ingredients that are available in abundance all over the world. And this compound can be then turned into highly functional construction materials with a variety of visual and mechanical qualities. ORB can be used for dry cladding, in interior architecture, as well as product and furniture design. It's shutting down. It's shutting down.
Bloody hell. Yeah, just carry on talking. I'll sort this out.
I might as well keep talking. So ORB can be used in for dry cladding of our walls, in interior architecture, as well as product and furniture design. And at the end of its life, ORB can be cold composted or returned back into our manufacturing processes to make more ORB. Our materials allow companies that we work with to deliver on their carbon targets as well as achieve their sustainable development goals. And for example, we're engaged with Google and the Restaurant Associates. And Googlers adore their orange juice and manage to produce around 3 tons of orange peel per week. So we have developed an orange peel-based ORB and designed a collection of products that we then give back to Google for use in their in-house restaurants. We also work with top designers to develop high-end products. And I had a picture of a very beautiful lighting piece that was exhibited last year at the Design Festival in Milan. So that's the lighting piece. And ORB is currently being developed further for use in exterior applications, as well as it will soon be transformed into a plant-based concrete. So the second material I'd like you to meet today is mycelium, or the vegetative root structure of mushrooms. So the fruiting body of mushroom is what we're all familiar with. Oh. Sorry, my videos are playing up. But the fruiting body of mushroom is the stuff that grows above the ground and many of us enjoy eating. However, mycelium is the hidden network that exists in the topsoil. And mycelium can be found everywhere. It's the nature's internet and the way plants communicate with one another and exchange nutrients. And as it grows, it consumes various organic substrates binding the topsoil. And our biome will harness this power of mycelia to develop and produce insulation panels. And we have collected a library of fungi species and working with over 300 of them. And our production processes are pretty simple. We pick a strain from our library, we expand it, we then introduce it to the substrate, which in this case is agricultural waste, and then we pack it into the mold. Our mycelium insulation panels have already outperformed many conventional materials on the market, and initial thermal conductivity tests have come back with a value of 0.024 WMK. Mycelium is also naturally self-extinguishing. I'm sorry, I had another video here. It's naturally self-extinguishing, and I had a clip from the BBC documentary where our mycelium panel was put through some experimental fire tests by Zoe Loughlin from the Institute of Making, and she was applying a blue torch on one side with about 1,500 degrees, which only slightly charred the surface, and she had an ice chalk on the other side which didn't melt at all and was, according to her, quite crunchy and enjoyable to eat at the end. And so our mycelium insulation and other products that we make out of mycelium have virtually no VOCs or volatile organic compounds. And at the end of its life, it can be cold composted or returned back into our manufacturing processes for us to use as a substrate, because mycelium is capable of consuming mycelium. Social sustainability is something that is central to all of us at Biome, and we have collaborated with the social enterprise, the Onion Collective, to establish the world's first community-led biomanufacturing facility in Watchet, West Somerset. Now, Watchet is one of the most disadvantaged towns in the UK with the lowest social mobility. And so with this facility, we aim to regenerate the local economy by providing jobs and sharing the profits with the local community. This facility is going to be operational from May 2020, and to start with, it will be producing 1,500 square meters of mycelium insulation per month, which will allow us to utilize at least 13 tons of waste and sequester at least 2.6 tons of carbon per month. Now, I do have another time lapse here, but I don't think it's going to play. Nope. So I had the time lapse of the building works at the facility, and this facility is designed to be completely closed loop, and any CO2 produced by mycelium as it grows is going to be looped into our greenhouse, where it's going to be turned into oxygen and then fed back into the mycelium incubation spaces. And we are growing very fast. We're now working with YMCA in Newcastle to set up our second facility by the end of 2020. And we are also launching an equity crowdfunding campaign towards the end of this month. And this is to invite our global community to take part in our vision and a journey. Last year, we have also won the Plant Plastic Prize from Waitrose and Partners, which has allowed us to continue our groundbreaking research into plastic-consuming mycelium strains. And now we have 5 strains that are capable of breaking down plastics such as PE and PU. And these champion strains basically are capable of micro-remediating complex hydrocarbons within the plastic and breaking them down into very simple non-toxic carbon molecules. Now, although we're capable to achieve rapid degradation rates in comparison to plastic life cycle, these little guys, they're a little slow at the moment, so we're putting them through a boot camp to make them stronger and faster and to eventually commercialize them, which will have a global significance because we'll be able to biorecycle waste streams from construction, fashion, and packaging industries. Now, all of our materials will eventually combine to form our revolutionary construction system, Triagami. And Triagami consists, another video? No? Triagami consists of building blocks that do not require any permanent fasteners or binders, which means that your home can shrink and grow in accordance to your needs, which will help us eventually transition towards agile communities and cities. We have been awarded for our work and recognized by many institutions. And we are working And we are working closely with the world's largest corporations, the world's top universities, and the world's most prominent governments, and of course, with local communities, local waste streams, local businesses, globally, in an attempt to deliver on a dream of biomimetic future, a future where industries are regenerative and work in symbiotic partnerships, where lands are nourished, where the waste is non-existent, where all nutrients are in constant circulation, where communities are prosperous, and where nature is flourishing. Thank you.
Thank you very much, Oksana. Sincere apologies for technicalities, but nonetheless a fantastically delivered presentation, so thank you. There'll be no doubt be lots of questions for you at the end. As an exemplar, I mean, you say designer, but designer, materialist, scientist, all kind of rolled into one. All right, so thank you. And similarly, I guess, I'd like to welcome Oliver to the stage. Oliver works at the University College at the Bartlett School of Architecture and has the title of Director of Technology, which is, fair to say, a fairly substantial title. And hopefully the technology isn't going to fail you, but I'm sure you'll be able to apply some directorial control over it.
Yeah.
Absolutely. So thanks, Oliver. And like I say, a reminder, we'll try our best to do some questions at the end. Thank you.
Lovely. Okay. Yep. Thank you for that kind introduction. Okay. So I'm gonna talk about some work that I've been doing with Cork over the past few years with people including Matthew Barnett Howland from CSK and research partners Professor Pete Walker from University of Bath, Andrew Lawrence, Gavin Maloney, Graham Flint Arup, and Nigel Jervis at Team Hour. Amarim supplied the cork, BRE did a lot of the lab testing. Just see if I can move this up. Okay, it's going to be quite a rapid tour of what we've been doing over the last 5 years, really. So a lot of contemporary buildings deliver the sort of performance we're looking for via quite complex means. Yeah. So you'll have elements that relate to structure, to thermal insulation, fire performance, internal and external finishes, that sort of thing. Yeah. For example, when we think about brick buildings these days, they very often have got an external brick leaf. They might have a concrete block structure or a timber frame steel structure, might have petrochemical insulation, lots of other things. And that introduces complexity over each stage of the building's life cycle. Yeah? And it often ends in this, which is destructive demolition. They're too expensive to disassemble. Yeah? So we had this, for this work, our aim was to deliver a different kind of construction system that gave us the current performance we're looking for from buildings, but did it in a much simpler way. Okay. On the right, this is our hypothesis that we could take cork and make a solid building envelope out of it that did all of these different things. Yeah. And that's what I'm going to talk about now briefly. So let's start off with the resource. So cork oaks have been growing around the Mediterranean basin for millennia. Cork is the bark of the cork oak, harvested about every 9 years, still using traditional methods. It's the outer bark of the tree, it's stripped without harming the tree and without causing significant disruption to the forest. These forests support significant biodiversity in the region. The prime cork is still mostly used for posh wine stoppers. You can see extracted there on the left. And that leaves a lot of byproduct from that industry and from others. The type of cork that we used for this work is expanded cork, and that's made using byproduct from other cork industries and also waste from cork oak forestry. Low-grade cork, ground up, put into an autoclave, here at Amarim in Lisbon on the left, cooked at over 300 degrees, and you get a nice freshly cooked cork billet coming out of there on the right. Yeah? So it's 100% plant-based, it doesn't have any other chemical additives. These billets need to sit around and stabilize for a bit before they're typically chopped up into insulation board, which is the main use. So this it's not a new product. Cork's been used for thousands of years. Expanded cork was invented over 100 years ago, and it's been used for things like wall insulation there in a Madrid slaughterhouse on the left, self-supporting partitions in a cold store, used extensively to insulate the White House when they refurbished it in the 50s, Caesar and Suter de Mora used it externally. First time the modern material's been used as an external cladding in 2000 for the Portugal Expo Hanover 2000, which was then moved to Portugal and still looks good today. Okay. So I outlined the team we worked with earlier, a mixture of academic and industry partners from across the supply chain, and we secured research funding from EPSRC and Innovate UK to proceed with this work, which ran from 2015 to 2018. So we started to think about cork as a bit like a sort of plant-based thermal insulative stone, and the aim was to develop a system that would enable us to simply assemble it, a bit like a giant toy construction kit, a bit like plant-based Lego. So as well as this being an idea for the wall system, we wanted to extend that to a roof system. So rather than using a different form of roof construction, the roof system we developed is a corbelled system, which is basically a wall, but you just offset each block a bit, and then you end up with a roof as well. Yeah? So you'll see this, there are examples of this all over the world, dating back thousands of years, in dry stone construction. So we got going at the Bartlett workshops, and things started to look reasonably promising, but you can see simple tongue and groove geometries to give a nice interlock. It's taken quite a lot of time to make these blocks, and the tolerance was quite challenging. So fortunately, we have colleagues at the Bartlett and kit at the Bartlett that enabled us to switch across to a robotic milling, and we developed a tailored robotic milling method to construct these blocks more quickly. Let's see if this will work. So this is a sped up slide of the robot cutting a roof block. There's a lot of hard work developing the method, but when it did work, which it did in the end, it took about 15 minutes to cut a block. Okay, so you can see there's no tool changing; it's all done in a single process. One big tool to do high volume removal, and using the edge just to put in the little details. Yeah? So there's the first wall. You might have noticed there was quite a lot of cork granules produced in that process. So we worked with Team Hour to produce cork lime terrazzo, and also to just make cork briquettes for burning in a solid fuel burner. Yeah? So the research included a lot of lab testing. We knew that cork was a good thermal material, but it's not normally used to keep the rain out. So we did a series of lab testing at BRE on wind-driven rain. And the wall system worked great first time around, so we were pleased about that. And the roof system didn't; it leaked. So we added timber weatherboarding on the inclined faces. Yeah, it was trickling through in the end, basically. And after that also passed with flying colours. We did a load of Pete Walker at Bath did a lot of structural testing. I won't be detailing that now, but that was a critical part of the work. We did quite a bit of fire testing at BRE too. Cork's flammable. It's a little bit like CLT, slightly more flammable. So you get a spread of flame, and it eventually self-extinguishes. So this gave us the data, the characterization that Arup needed to engineer the projects that we went on to do. We also built a test building, cork cabin, assembled in the Bartlett on the left, disassembled, transport to site and reassembly. So that also gave us the chance to test and demonstrate the design for disassembly concept. It was very easy to disassemble and then put back together again. There's us putting it together on site. Each block weighs about 12 kilograms, so it's fairly easy to assemble. Here's the cork cabin and a smaller test building too. On site, we did a range of testing, thermal and humidity testing, find out what was actually happening in the depth of the wall. We did standard building regs air pressure testing, and we were pleased that it passed the test. And so after this time, we'd got a system that kind of worked, that we were then ready to apply to a live project. So cork house. So fortunately, I was working with Matthew Barnett Howland and Dido Milne on this. They funded the project. Matthew also built it, so we're very fortunate to have people to work with that let us get straight on with a proper building after this. Yeah. So here's a cork construction kit, which we use for the house. It's all dry assembly. There's no cement or mortar. There's no on-site gluing together of components. It's all dry connected. Screw piles, timber deck, cork wall blocks, timber ring beam, cork roof, roof lights on top that help to stop it blowing away. It's not connected down at all, it's just dry assembled. This is the house. It sits on a small island on the Thames between two existing gardens, acts as a kind of gateway. 5 pyramids, each with particular programmatic functions. This is what it looked like when it was assembled. So you can see it's nestling in there. There's a Thames pumping station sitting behind it. You can see that the cork naturally silvers over time, as does the cedar. So it all sits quite comfortably together as a palette of materials. You can see the roof lights on top there that hold it down and let in plenty of daylight. It's almost kind of temple-like internally. You can feel the load-bearing structure. It's also very pleasant internally. Smells good, calm acoustic, well daylit. So this is the life cycle. Forestry product, using waste and byproduct to make a pure plant-based block, dry assembled on site. At the end of life, easy to disassemble for reuse or recycle into manufacturing, or because it's pure plant-based, it can go straight back into the biosphere as well. Last couple of slides. So we got a whole life carbon assessment done. Sturgis carbon profiling indicated it was slightly carbon negative at completion because of the carbon locked into the plant-based materials. And then shipping that across from Portugal burnt about half of the carbon we'd locked in, but it still came out as carbon negative. And whole life assessment indicates very low embodied carbon over a 60-year life cycle, also low operational because it uses logs from tree maintenance on site to heat it. That's the main reason, yeah? And some comparisons to some other building types. So we're now moving forward with this general approach, form follows life cycle, to investigate some and develop some other low carbon, simple forms of building. Thank you.
Brilliant. Thank you very much, Oliver. I mean, again, there'll be loads of questions. I guess what really strikes me is this, having worked in sustainability for quite some time, is there's a lot of sort of implicit notions of how sustainable design relates back to sort of nature. But actually, a lot of what we do is really just mitigating human behaviour. It isn't really engaging directly with the benefit of species and so on. But I think in each of these cases, your propositions really do. There really is a channel that connects back to improving natural systems, which I think is something to really, really celebrate. But what a fantastic technical project. Thank you very much. Okay, so next is Alex. Alex is with us. Hi, Alex. Thank you. So Alex is from Hempcrete. We've done some projects around flax and so on in the past, so I'm very interested to hear more about your proposition. Alex, everybody's sticking to time, so we should have some questions. Thank you.
Hi there. Can you hear me? Yeah. I do like being fourth because it means that a lot of the people who come before me have covered a lot of the relevant science, and I can just get on and show you some pretty pictures. So my company, UK Hempcrete, we specialise in, we're known for hempcrete, which is not exactly a new material, or relatively, I suppose it's new. It's been around for about 30 years. We've been building with it in this country for 20 years, and my own practice has been over the last, just over a decade. But we also work with a range of other natural materials that complement hempcrete. So, sorry, what am I doing? And that would include other plant-based insulation materials and construction materials. So typically we're using a timber structural frame and then hempcrete, wood fibre insulation, cork insulation, a range of natural finishes, lime, clay, etc. So just up on the left there, that's UK hemp growing in Yorkshire, and that's then harvested, processed to separate the bast fibre, which is used for textiles and a range of industrial applications. And that bast fibre is separated away from the stem, which is the woody part on the bottom right that you can see, which is what we use for an aggregate in hempcrete. The bottom left is hemp fibre insulation. actually made by Mark's company, being installed in a roof. So that's an application from the other part of the hemp stalk. So hempcrete itself is a mixture of the woody stalk of the hemp plant mixed with a lime binder. And you can think of it as a kind of loose fill material that then sets and holds its own shape. And it's used as a walling material, as a roof insulation, a floor insulation. It's used as an insulation to add to existing masonry walls as a solid wall insulation. Basically anything you can it can be cast in shuttering or it can be spray applied. Basically it's a material that will go into any shape void and then set. Okay, so this is just showing you a few of the different applications. You can see in the bottom left where we're combining it, that's the top of a hempcrete wall with tongue and groove wood fibre board insulation over the top of the rafters, giving you a nice airtight seal over the roof. And just at the top left of that bottom left photograph, you can see the space between the rafters, which is going to be filled with, in this case, sheep's wool insulation. Okay. As well as hempcrete. Am I pressing the wrong delay? Sorry. Yeah. So this is just to demonstrate, as well as hempcrete itself, we're using a lot of other recycled and bio-based insulations along with it. So the bottom center photograph is foam glass gravel, which is used as part of it's a recycled glass product that's used as a free draining aggregate underneath a lime sand screed. And I've only got a couple of data-driven slides, but this is quite an important one, so hopefully you can read that. So this is really just summing up the performance of hempcrete because it's a little bit unusual. So hempcrete, because it has usually in walls, it has a density of around 300 kilograms per cubic meter. So compared to other insulation materials, it has a lot more thermal mass. It has a higher specific heat capacity than other insulations, and that allows a sort of almost unique thermal performance, really, in being a mixture of insulation and heat storage within the same material. And so the top row is the thickness of the hempcrete layer in centimeters. The row below, obviously, the density, and then the row below that, the U value that you would expect from that thickness. So that you can see when we're building new build hempcrete walls in this country, we're casting hempcrete usually between 30 centimeters, 300 mil, and 400 mil thick to achieve a U value that passes building control. But the important thing is that because of if we drop down a couple of rows, the specific heat capacity there means that the U value is not the end of the story when it comes to hempcrete's performance. So as Mark was helpfully explaining to you earlier on, what we're aiming for is a long phase shift time, okay? So you can see if you look at the phase shift times, which is the bottom row in that table, and then you compare that to the thickness at the top of the slide, what you'll see is that hempcrete at around 200 mil, 20 centimeters, has a phase shift time of around 12 hours. So at that thickness, what you get, as demonstrated by this piece of research that was done by Bath University in 2006, what you get is a flattening out of the external temperature, day-night temperature changes, because this is showing 200 mil of hempcrete around a timber frame, the purple line showing the day and night temperature changes, and the red line inside showing the internal temperature in the building with no heating at all. Okay, so because of that phase shift time, that heat buffering is basically flattening out, buffering out the temperatures the temperature changes in the environment. So all of this, I think, it's just a delay, isn't it? So all of this makes hempcrete quite a popular material. So as I say, we've been building in this country for 20 years now. There are hempcrete housing estates dotted up and down and around the country. There are lots of hempcrete commercial buildings. My own company does a lot of domestic scale projects, some commercial subcontract. So we're working predominantly in the domestic sector, where you tend to get early adopters who know what they want and why they're spending the money to get a particular performance from particular materials. This is the type of kind of internal finish that we're getting in our buildings. So this is typically with a lime plaster, clay plaster, lots of the finishes for hempcrete, as can be seen on the previous slide. The finishes would typically be a lime render, but can also be timber clad or clad in masonry using a lime mortar. So the key thing is that the whole building envelope is vapor permeable, and as Mark said earlier, that helps to passively regulate the internal humidity in the building, as well as allowing moisture that we create inside the building to pass through the envelope and keep the building fabric in good condition. We also use hempcrete in the retrofit and renovation of older and historic buildings. I'm not going to focus too much on that today. And I just wanted to take you through the sequence of us building up the fabric of a new build house. So in this case, we're using a combination of precast hempcrete blocks internally as an internal skin, and then we're wet casting hempcrete on the outside of that to give a continuous single piece of material around the outside of the building. So the benefit of having the precast blocks internally is that the internal skin is already dry before it comes on site, and that means you can move ahead with fitting out the building while the outside skin is still drying. So we first build a timber structural frame. We apply that skin of blocks internally, and you can see there that's the structure with the blocks applied, waiting for the external hempcrete, which is then mixed on site in a large pan mixer. It's really simple, shuttering up the outside of the building, filling that with the cast hempcrete, which gives you the benefit of this single external layer, avoiding any thermal bridging, meaning that you've got a single piece of material to plaster and make airtight. You can see there that the two layers together in the envelope of the building, and this I think demonstrates the advantage of the cast material, that you get this single piece that fits very closely to the building's frame. We then finish the hempcrete installation, leave it covered for the other contractors on site who are doing the roof installation. Roof build-up was recycled wood fibre insulation. So the building gets roofed while the external and windows go in while the external hempcrete's drying, and then we come back to install the lime floors and the internal lime plaster, and then eventually the lime render externally. Okay, got I think probably 30 seconds more, so just to show you the same concept in a commercial build. So this is timber cassettes inside a steel frame building, hempcrete blocks installed on site, and then the outside of those cassettes is wrapped in wood fibre insulation, taking in the steel frame and the timber frame, and that is in some on the gables of the building is brick clad. And then other elevations of the building, the lime renders applied directly onto the wood fibre. And the reason for doing that is it's just a little bit easier in a commercial scale project not to have the wet installation of hempcrete on site. So thank you.
Thank you, Alex.
Last slide. Not working, but never mind.
Thank you very much indeed. Again, another fantastic delivery, so we are definitely going to have time for questions for you, Alex. Thank you very much. So finally, John is joining us. Thanks, John. John Thorogood is joining us from Grafenstone, UK. And one of the materials John is hopefully going to talk about is graphene, which is seen as one of these kind of revolutionary, transformative materials. So I'm really looking forward to hearing a bit more about that.
Okay.
So thank you, John. I'll give you a 2-minute warning. Thank you.
Good morning to you all, and thank you so much for your time today. Grafenstone is the brainchild of a chemical engineer who dedicated himself to the idea of developing a natural, ecological, and health-conscious coatings for the 21st century. Thank you. After much research and testing, Antonio Jimenez has succeeded in developing paints that harness graphene technology from the Nobel Prize-winning scientists of Manchester University to deliver mineral paints that are simply unmatched in health and durability. Over the last 100 years or so, technology and innovation has moved mankind forward at a rate never seen before. Through industry and invention, we have become obsessed with finding ever more increasing ways to speed manufacturing up, to produce materials that last longer, and generally just pushing the boundaries of what is possible in our aspects of life. Unfortunately, this is often at the cost of our environment and ultimately our planet. The negative effects from burning fossil fuels, plastic waste, and pollution are now clear for all to see. Freak weather patterns, rising temperatures, glacial retreat, rising sea levels, floods and droughts, just to name a few. The images of the recent bushfires in Australia are a harrowing snapshot into the issue of global warming. More alarming still is the increased frequency and ferocity of these global events and their impact on all life on Earth. A less visible but obvious major effect of global warming is poor air quality. This has generally been overlooked until recent years, and there is now an accelerated urgency to improve our air quality indoors and out. A recent study by the World Health Organization claimed that indoor air can often be 2 to 5 times more polluted than that of outdoors. Another report by the Royal College of Physicians claimed that air pollution is contributing to about 40,000 early deaths a year in the UK. We are all challenged to stem the momentum of climate change. It is up to us. It is our responsibility. And one of the biggest changes we can make is the reduction and release of VOCs. Paint selection can play a major part in this, with most having high levels of formaldehydes, benzenes, CO2 and other volatile organic compounds known as VOCs. These VOCs are released into our air during the drying period and for many months thereafter, meaning that this toxicity remains in our spaces for a significant time with potentially disastrous consequences. To put this into perspective, a World Health Organization study claimed that professional decorators are up to 40% more likely to contract lung cancer due to their constant exposure to these VOCs. When these VOCs react with oxygen, they produce bad ozone, which contributes significantly to the greenhouse effect. Modern acrylic paints are also not particularly breathable. They can seal in moisture behind the paint film, and this moisture can lead to fungus, mould and bacteria, all of which are highly damaging to human health. The British Coatings Federation claims that 700 million litres of paint are sold each year in the UK, and the Environmental Protection Agency classifies paint as one of its top 5 most hazardous substances. But now, a new advanced option is available. Better results, yet completely natural and sustainable. This is because we add graphene to our products. Graphene is a remarkable material that was first discovered in 2004 at the University of Manchester and later won the Nobel Prize for Physics in 2010. The physical properties are quite remarkable, space age almost. 200 times stronger than tensile steel, 1,000 times more conductive than copper, and 20% flexibility without cracking. At Grafenstone, we have weaved graphene throughout the molecular structure of our natural minerals to give these once brittle materials a structural support mesh, holding everything together. This means that our 100% natural, sustainable paints are now Class 1 strength for the first time, and quite uniquely elastic, meaning it will resist cracking and flex as buildings move. The structural support from graphene also means the paint feels like a normal paint to apply, something certainly not usual with lime paints of the past. All of the advantages of adding graphene, coupled with the advantages of the natural materials, means we finally have a product range that meets our needs without the toxicity. The raw material for our product range is pure limestone. It is 100% natural and sustainable. It has zero VOCs, acrylics, formaldehydes, benzenes or plastics of the more often used trade paints. Absolutely zero toxicity. The wonderful part of this material is it absorbs carbon dioxide at a rate of approximately 4.8 kilos per 15 litres of paint. After painting, calcium hydroxide cures on the wall, and as it cures, it absorbs CO2 and becomes calcium carbonate. That chemical reaction essentially turns the paint back into limestone, and it absorbs CO2 on its journey to do this. Our paints, due to the lack of toxic ingredients, has no real smell. It is also a naturally high pH of 12.5, which means nothing likes to grow on it, taking care of any potential problems with algae, mold, fungus and bacteria. The paint is naturally fire retardant to Class O, the highest standard available. And being a natural mineral, it is completely vapor permeable. It allows buildings to breathe and lets moisture pass freely through it. Great for heritage properties and great for new build construction. So this is the basis of our paint, free of the toxic and environmental disadvantages of the regular trade paints, but with numerous advantages of naturally occurring in these materials. The addition of graphene takes nothing away from these advantages, but enhances the performance drastically by adding strength, durability, flexibility, and homogeneity. This all results in the perfect mix: tradition, innovation, and technology, creating paints that meet the demands of modern life in a far more natural and sustainable way. Surely this is the ultimate goal for all of us. So to summarise, our paints offer exceptional opacity with up to 70% solid content. They are fully breathable with SD ratings from 0.02. They offer traditional, ultra-flat and modern washable finishes, all with Class 1 strength. They have zero toxins and are free of VOCs, APEOs and MIT preservatives. They give excellent yield of up to 18 square metres per litre. They are fireproof to Class O, the highest rating available for prevention of spread of flame. They protect against fungi, mold, algae and bacteria. They are uniquely elastic and flexible, resulting in almost no cracking. And most significantly, they absorb CO2 at a rate of up to 5.5 kilos per 15 litres with no off-gassing. To help you visualise this, if this entire wall space, approximately 87,000 square metres, was painted with our lime paints, around 2 tonnes of carbon dioxide would be absorbed. That's about the same weight as a large family car, but in the form of a gas. Grafenstone's commitment to the environment dictates the use of natural, ecological materials. Our core values are ecology, nature, sustainability, and respect for the environment. Our factory in Spain is powered by 100% renewable energy, and we use non-polluting raw materials and recycled wastewater. Our paint containers are made from 80% recycled plastic and are 100% recyclable. And our packaging is made from recycled materials. Our products meet the principles of a circular economy. That is why almost all of our paints carry either the gold or silver cradle-to-cradle certification. Cradle-to-cradle certified products have undergone scientific material health assessments down to 100 parts per million of its materials and its ingredients. Product packaging, the chemicals in water, renewable energy, CO2 compensation, social fairness and cyclability are all scrutinised. Nothing is ignored, and everything is revisited to constantly improve the standards towards planet-healing products and practices. And in line with the philosophy of Grafenstone, our products contribute actively and positively to the fulfilment of different criteria of the most recognised sustainable building certificates worldwide, such as LEED, BREEAM and the World Building Standard. The benefits are clear for all to see. improved air quality, sustainable materials and practices to the highest standards, less waste, and working towards a circular economy. We are without doubt the most eco-friendliest paint company on the market today, and we have been accredited accordingly. On our website, you'll find an exhaustive list of certifications, some of which I have mentioned, and the numerous awards we have won around the world. So to sum all this up, if there was a time for us to step forward and change things for the better permanently, it is now. This is the challenge the whole profession needs to get behind. Collaboration is required for us all to meet and embrace the desired target of circular construction. The research and technology exists for us to begin this transformation now, but what has been lacking is the collective will. For many years, sustainability has been perceived as a cost increase rather than a value enhancement. But there are signs of change, a growing desire to turn it around. We at Grafenstone see ourselves as a big part of that change in culture by offering paints for a greener generation. Thanks very much.
Brilliant. Thank you, John.
Thank
John,
you.
can I get you to take a seat here?
Of course.
We're very fortunate to have some time, so if all of our speakers would mind coming back up to the stage. Yeah, sure. So Duncan, my friend who's exceptionally fit, is going to prance up and down with the microphone for those of you who'd like to ask questions. So a rare opportunity to get this many materialists in the room together. So would anybody like to ask a question? Yes, sir. Just here. Thank you.
Oh, does it work? Okay. Thank you for your talks. I was just wondering if you feel the materials you're representing are applicable to developing countries and if they'll be readily accepted by them as well.
So good question, thank you. So the accessibility of your materials and technologies in developing countries. Would anyone like to step forward on that? Thank you.
Hi. Speaking just about hempcrete specifically, it's quite accessible all over the world, mainly because it's quite a low-tech solution. So it's a bioaggregate, a plant aggregate that then gets mixed with a mineral binder, which is, as it moves around the world, hemp itself grows all over the world in quite a wide array of different climates, unless it's a really arid climate. But what you find happens as the technology moves around the world, the bioaggregate changes to whatever the locally available waste bioaggregate is. So hempcrete, or a version of it, has been made with coconut fiber, with rice husk, sugarcane, bagasse, and typically the binder itself changes as well, depending on what minerals are available locally in the geology.
Oksana, do you want to come in?
I'd like to add. Hello. Yeah, the same goes for us. So at the core of all of our materials are local waste streams as well. So wherever we go, we use whatever's available. So it's organic and agricultural waste streams for our sheet material. And the binder that we have developed is made of edible materials. And again, they have been selected so that we could find them anywhere we go when we scale around the world. And for mycelium products, the same goes as well. So it's agricultural waste streams. Anything that has lignin in it would do well as a substrate to grow mycelium. And again, we use local fungi strains to feed the agricultural waste too.
Mark, I was going to ask you, I mean, again, you're very expert you have a long-standing expertise in these areas, and I wonder are you seeing some of this knowledge transfer? I mean, you're always very generous in helping to impart your knowledge out to the wider community, but are you seeing a kind of a global take-up on these kind of natural materials and fibres?
We get a lot of interest. Just to echo what the previous speakers have said, it's just a question of using what materials are available locally.
Yeah.
Find the right analogues for that. The difficulty challenge you face when it comes to insulation specifically is finding the facilities to produce. And I think the key to that is to find industries that are producing similar materials, products, and to start by toll manufacturing and really jumping on the back of other industries, because of course there's much less impact in using spare capacity somewhere than there is in building new capacity.
Indeed. And again, with some of our collective research, and obviously some of you have worked with Bath routinely, we've been exploring this notion that there are lots of agri-businesses out in the world that may need to adapt to climate change or new models to support their businesses at a time when agriculture is changing itself. So they may well be very receptive to working with heavy plant machinery in kind of productive cycles. So the farming community worldwide may well be a place in which we could enact some of these opportunities. I think that's fair.
Yeah, but I do think the fundamental is that, you know, if initiatives are going to have legs long term, they have to be founded as a business and run as a business, and not a, you know, it's got to have legs from a commercial point of view, regardless of where it
has to be an
is
economic
located.
driver too. Yeah, of course. Okay, other questions? Yeah, I'm going to. Thanks.
Jeff Cooper, just a very quick question to John. How does your paint react on already painted surface?
Was that how did the paint react on already painted surfaces? It's absolutely compatible. Standard preparation rules would apply. So as long as the paint was sound and well adhered, our product would go straight over the top of it. What it wouldn't do is increase the breathability, because obviously what is on there is the limitations of that. But there is no issues with going over existing coatings, and likewise putting other coatings over ours either. So it's completely compatible both ways, which I think is a very important question to answer. So completely user-friendly.
Thank you. Thanks for that. Oliver.
Hi. Fascinating talks. I can see that there's a rise in interest in carbon-centered approaches to building design, and at the same time, human-centered benefits as well. Could you just talk a little bit about the choices that your clients are making in order to come to use your products? Are they thinking about carbon, or are the human-centered benefits kind of driving forwards, going, yeah, these products make sense for the spaces that I want to live in?
From a paint perspective, I think the painter and decorator part of the equation is still a little bit slow to take it on board. I think the change in what people are purchasing is very much driven by the end client, whether that be a large construction client or a residential retail customer. So the general inquiries that we would get would be somebody who is very eco-driven would be one route, and also somebody that's interested in indoor air quality, of which our products do tick both. But my background prior to working with Graftonstone was multi-paint branded, and I've been doing that for about 11 years, and I've seen a massive change in what the initial inquiry is for. So there is definitely a shift between what's becoming important to people, and I think obviously probably 2020 is the year of sustainability, and I think that's probably the reason people are finding Graftonstone in particular. But like I say, the trade element in the middle is probably the last part to catch on to that. It's very much being driven by the end user.
I think most consumer purchases are evolving now, so it's more centered around the sort of holy trilogy of healthy for me, healthy for my home, and healthy for the planet, and maybe not drawing a specific distinction between what's eco and what. In particular, I would say probably a third of the people showing an interest in our kind of products, their primary driver would be health. A third would be sustainability. You know, but as I say, people are moving towards a more holistic approach to things.
Alex.
Hi, yeah, just to echo what Mark's saying, but also we sort of see three groups really in our customer base, and there is a lot of overlap, but those would be typically people who are very concerned about the building in a way that's low impact and carbon sequestration particularly. I think over the last 5 years there's actually been a big increase in the understanding that zero carbon buildings is not just about operational energy, it's about the embodied energy of the building fabric itself. The second group is this, rapidly increasing sort of understanding, as Mark was saying, of the health implications of the materials that we use in our building fabric, especially when it comes to things like paints, which are on the surface of the construction. And then the third group is people who are concerned with, particularly with the vapor permeability of the building fabric, possibly because it's in the restoration of historic buildings or just because they want to create healthy new build.
Okay, thanks very much. So lots of questions still. Right down the front here. Yeah. Sorry. I think you were first.
Thank you. Really brilliant talk. Fantastic materials. Brilliant. We have a company. We are a building company, but most of our clientele are basically more interested in value for money, basically. So it's typical.
Celotex and products like that.
So I would like to obviously go plant-based, natural, but how can we compare the cost, obviously going into cheaper product, because we would love to obviously go more health. So how do you go more mainstream? How can we compare, sell this to the client?
It does. We've got very little sound on the monitor here, so
for money.
The cost, basically cost comparison with conventional construction. Yeah. So I'll just very quickly, from my point of view, as you can see from my slides, the market that we're predominantly in is kind of bespoke one-off houses. In that market, we are pretty much exactly the same as any other construction material to a high standard of insulation and airtightness, which tends to be what people in that sector are getting for their money. Now, if you challenged us to build at £800, £1,000 a square metre to, give Persimmons a run for their money, we're not able to do that. But equally, nor would we want to, because what we're delivering is something that is a significantly different product than what is being built at scale in this country. The comparison that I've just given you, we do need to look at ways, we are currently looking at ways to scale our construction methods up into scale house building, for example. But the question is, even when we are the same price in the domestic sector, you're still only talking about build cost, which is all that anybody wants to talk about in construction in this country. So when you consider that a hempcrete house with no heating whatsoever will maintain temperatures of 16 to 18 degrees centigrade solidly throughout the year, the cost of running the building over the lifetime of the building makes the way that we build much cheaper. Never mind the cost to the planet of the embodied carbon. So it's really, I think you're asking the right question, but what we need to do as an industry is kind of reframe what we're doing when we are marketing the housing, for example, and the buildings that we are constructing to show so that clients know what they're buying and why the build cost, for example, is not the only thing to be thinking about.
Oliver, could
I've just a couple of things there. I mean, it's interesting. Obviously, there's a tendency to use the cheapest product that gives the performance. I mean, interestingly, Celotex used to make plant-based boards. That's where they got the name from. Yeah. Cork insulation used to be marketed in the first half of the 20th century, a bit like Celotex is now. The cheapest, most insulative material, and it was until after World War II when these petrochemical foams became cheaper and more insulative. Yeah? So it's quite interesting to see how they've come in on that trajectory. But yeah, just following on from the last point, I mean, one thing to consider is to look at whole life cost as well as whole life environmental sustainability issues. And certainly, we started to move towards those models, particularly for people who are owner-occupiers, then that would start to change, influence decision-making in a positive way.
Okay, we kind of need to wrap up now, but I'd like to welcome everybody to thank our fantastic speakers again with a round of applause. Thank you. I think we're all kind of materialistic in our own way as consumers, and several commentators have said we're not nearly materialistic enough, and I think all of our speakers today have really helped to give us an insight into how materials are really central to a lot of these kind of concerns. So thank you very much to them. I'm going to hand over to Duncan, who's going to promote the 12:30 keynote. Thank you.
Yeah, thank you to everybody. We've got a keynote at 12:30 that I'm really excited about. It's Harry Paticus, who's one of the UK's leading architects dealing with genuinely interesting and considered retrofits. So the adaptation of the existing stuff to meet our low carbon ambitions and our net zero targets. So come along here at 12:30 and hear our keynote, Harry Paticus. Thank you very much.
Everybody, thank you.